if you push with a 10 Newton force on this block, what's the magnitude of the static friction force? Now, I hope you didn't do it the wrong way. The wrong way would have been to say, oh, that static friction is mu s mg, or you might have reasoned mu s times the perpendicular force, and in this case the perpendicular force is mg, and that gives you 30 newtons. No, that is incorrect, because the force of static friction is not mu s times the perpendicular force. That's the maximum static friction. All that's telling us is that whatever this static friction is, it had better be less than 30 newtons. So the correct way to do it is to realize, well, the block isn't sliding, its acceleration is 0, and so the vector sum of forces must be 0, and so the static friction must be exactly canceling the 10 Newton force that you're exerting to the right. It must be 10 newtons to the left. Or in other words, you could set up your axes, you could draw your free body diagram, looking at it, you could do your x component of the equation of motion and just solve that for the force of static friction, and you see that its magnitude is equal to the magnitude of the force that your hand is exerting on the block. Now let's understand why the static friction and the kinetic friction work so differently. And to start, we're going to look at a completely different force. We're going to look at the perpendicular force between, say, a plank and a brick sitting on that plank, because it turns out that it behaves rather similarly to frictional forces. So imagine that the brick is just sitting on the plank, and we know that there's an upward perpendicular force due to the plank acting on the brick, and that it balances the downward gravitational force on the brick. Now, if you press down a little bit on the brick, then the upward force by the plank has to increase because the acceleration of the brick is 0, and so the vector sum of forces still has to be 0. And so that force increases to maintain a vector sum of forces equaling 0. If it didn't, then either the brick would accelerate down through the plank, or it would accelerate up off of the plank. We certainly don't expect either of those things to happen. If you press harder, then it'll increase further. And note that the plank is bending. It was actually bent a little bit right at the beginning just because of the brick sitting on it. But you probably wouldn't notice until you'd pressed rather hard down on it. But these are all reversible deformations of the plank. If you take your hand off, it'll restore to being approximately straight. However, if you press very hard, you may be able to break the plank, and that is clearly an irreversible process. At that point, the upward perpendicular force due to the plank ceases to exist. The frictional force actually works almost exactly the same way, so let's go back to the brick on the plank and you not pressing on it. But now we're going to have to think about how things look at the microscopic level at the interface between the brick and the plank, where they are in contact, but they're only in contact over a very small fraction of their surfaces. Even seemingly smooth surfaces are actually quite rough on the microscopic scale. And now, as I go forward, I'm going to omit the vertical forces for simplicity and clarity, so we can just focus on the forces that your hand is exerting horizontally and that the plank will exert back horizontally on the brick. So first, when you start to push a little bit, there is a horizontal static friction force that exactly balances the force that your hand is exerting. And if you press a little harder, that static friction increases to compensate. Again, the vector sum of forces is being maintained at 0 by this force. And there's still deformation, reversible deformation occurring, but you would probably never notice it because it's going on at the microscopic scale of the surfaces. But now exactly the same thing happens as before. If you press very hard, then the surfaces actually break. They start chipping and gouging each other and causing irreversible state changes. And this is what the kinetic friction is. The two surfaces are now sort of skipping over each other, occasionally bouncing off of each other and doing damage to each other as they do so. In the case of the perpendicular force, when the plank broke, that force disappeared entirely because the plank would have fallen away and no longer been in contact with the brick. With the friction force, there's now intermittent contact between them, and so there is still a force. However, it's smaller than the force that was occurring when the two surfaces were in good contact. Additionally, there are various other things going on that are very complicated. When a static friction is acting between two surfaces, often those surfaces are actually weakly molecularly bound to each other with hydrogen bonding and all sorts of other things. And that's another part of the reason why the static friction force is larger at its largest limit than the kinetic friction that replaces it once the surfaces start sliding across each other. When an object rolls, there's some compression that goes on at the front of the contact and some re-expansion at the back of where the object is in contact with the surface that it's rolling over. But this is not totally reversible. The re-expansion doesn't quite undo the compression perfectly, and so that means some energy is dissipated in this process, and a wheel or ball or something rolling along must slow down gradually because of dissipation. And because it's slowing down, that tells us there must be a force back against the rolling, and this is a rolling friction. But notice that these rolling friction coefficients are very small, and so that tells you that forces of rolling friction are also very small, and so we can pretty much always ignore them for our purposes, and we will. One of the reasons I'm not putting more emphasis on this topic is that these models of friction are approximate. So we have these models that the kinetic friction is proportional to the perpendicular force by the same surface, and the proportionality constant is called a kinetic friction coefficient, and that the maximum static friction has a very similar formula with a static friction coefficient, and these are both independent of contact area. And I didn't say so, but also somewhat counterintuitively for most people, these forces are independent of speed. But this whole model is approximate. It holds approximately some of the time. But sometimes these do depend on the contact area or the relative speed of surfaces. And it's not always strictly proportional to the perpendicular force. And these friction coefficients aren't constants at all. They're rather variable. They depend on temperature and all sorts of other things.